Hello, my name is Oliver Verdickt. I'm the regional manager for Soprema in Australia and New Zealand. Today we are going to talk about warm roofs. So welcome to the Equus Soprema warm roof CPD presentation. Before we talk about warm roofs, let's have a look at cold roof construction. In a cold roof construction, we see that the thermal insulation is located under the roof structure. In between the roof structure and the thermal insulation, we have an air cavity. This air cavity is ventilated with outside air. This means that an external temperature can come into contact with the internal temperature, which in some cases creates a dew point. Now, this may lead to internal or interstitial condensation between the layers of the roof structure, creating humidity, creating moisture problems. For that reason, we need to ventilate that air cavity, which can be done by cross ventilation or by ventilation through the roof. But this might lead to other problems. Another issue with a cold roof is that it needs to keep the insulation dry also from the humidity created within the building. When we use a building, we create moisture. That hot and humid air rises, and we need to separate that from the thermal insulation. For that reason, we need a vapor control layer. The vapor control layer, however, on the inside of the building is not always easy to make airtight, because again we have walls and columns and other penetrations. Finally, if we put the thermal insulation under the roof structure, we don't have a continuous insulation layer because it is interrupted by again those walls or columns or other penetrations. This all creates temperature bridges, and each of these temperature bridges will take away some of that R value or thermal resistance for which we put thermal insulation in that roof concept in the first place anyway. So how can we solve all of these issues that we encounter with a cold roof? This brings us to the warm roof concept. In a warm roof concept, the thermal insulation is placed above the roof deck. The vapor control layer is also placed on top of the roof structure, in between the roof structure and the insulation. The insulation itself is protected by a waterproofing membrane system that's placed on top of that insulation to protect it against the external climate. The warm roof system that combines vapor control layer, thermal insulation and waterproofing membranes is a lightweight system that can be placed on a whole range of roof structures, such as, for example, concrete, corrugated metal, plywood, CLT timber, or in some cases even an existing roof. When we place the insulation layer on top of the roof structure, we will be able to make a continuous thermal insulation layer. We don't have to deal with the internal walls and columns. In that way, we can reduce the temperature bridges. By doing this, we have now more control over the performance of that thermal insulation layer. Internal air and external air will now be separated. They can't meet each other anymore on the inside of the roof structure, so there is no need for an internal roof cavity that needs to be ventilated. This makes the design much easier. What we can also say is that by placing the vapor control layer on top of the structure, we are now dealing with an airtight system that can help us to control the internal temperature much better. A warm roof stabilizes the internal temperature, which then helps us to save energy, because we start to cool down or heat up from a more modest temperature inside. Now this energy cost saving is the return on investment for the building owner. So simply said, a warm roof is a simpler, smarter, healthier and more energy cost saving friendly concept compared to a cold roof. A warm roof system is composed of different elements. We already mentioned them in the previous slides, and here we can see them once more. On top of the structural deck, we have a vapor control layer or vapor barrier. On top of the vapor barrier, we have the thermal insulation boards. And finally, those thermal insulation boards are protected by a waterproofing membrane system. The first layer in a warm roof system is the vapor control layer or the vapor barrier. This vapor barrier has several functions. The most important functions, in my opinion, are to encapsulate the thermal insulation and protect it on the long term against moisture. And secondly, it can also be used as a temporary waterproofing during construction. When we look at the design of the vapor barrier, we see that at the sides of the roof it is connected to the waterproofing system. This basically forms an envelope around the thermal insulation and keeps the insulation dry against rising moisture from humidity generated within the building. As a temporary waterproofing, the vapor barrier can be installed on the structural roof deck and can remain there for a while other building works continue. Eventually, the applicators will place the thermal insulation and the waterproofing to finish the warm roof system. The vapor barrier can also have other functions. On top of keeping the insulation dry and protected against moisture, it can also have the benefit of a sound insulation. In this case, we can replace the normal vapor control layer by a mass-loaded barrier that helps to keep the outdoor sounds out and give a much more friendly sound-insulated space below. The second and most important component of a warm roof system is the thermal insulation. A popular thermal insulation type is polyisocyanurate. Polyisocyanurate boards are composed of an internal core of polyisocyanurate or PIR and are finished on the top and at the bottom with a facing. A regularly used facing is, for example, the multi-layer complex aluminium. These boards have what we call a thermal conductivity coefficient or lambda value. This is an important figure because it dictates the actual R value of a certain thickness of an insulation board. When we look at PIR, you can see that you need thinner boards in order to get to the same R value when we compare it to other insulation materials. We also see that the PIR boards have a high compressive strength. This is important because we have to allow that roof maintenance traffic can proceed on top of the waterproofing system where the insulation board is located under it. So this means that people have to be able to walk on top of the warm roof concept for regular roof maintenance activities such as cleaning out the gutters or checking the waterproofing condition. The PIR boards are rot-proof, fire retardant and mold resistant. So when we combine all these characteristics, we can now understand why it is used often as part of a warm roof concept. Another type of thermal insulation that can be used within a warm roof concept is stone wool or mineral wool. This type of insulation has different characteristics compared to polyisocyanurate. First of all, it is non-combustible. Where PIR is flame retardant, meaning that it prevents spread of flame, we can say that the stone wool is totally non-combustible, meaning that fire does not affect the shape or form of the board. The disadvantages of mineral wool, if we may say that, when comparing it to PIR, is that it's much heavier, almost factor 10. And you will need thicker insulation layers in order to get the same R value compared to PIR. I can show that to you in the following table. This table shows a sum of the product characteristics of mineral wool and PIR. If we want to obtain 6.6 R value, for example, with a PIR board, then we will need a layer of 150 mm thickness. Do we want the same 6.6 R value in a mineral wool, we will need at least 250 mm of insulation. This means 100 mm of insulation more, which of course influences the cost of building. On the other hand, if we look at 6.6 R value for PIR, we are talking about a weight of 4.8 kg per square meter. If we would look at the weight of mineral wool to obtain the same 6.6, we are talking about 45 kg per square meter, so almost factor 10. So there are some significant differences between PIR and mineral wool. In some cases, we add an optional layer in the warm roof system. We didn't talk about that until now, but let's say that you have a very technical roof. What is a technical roof? It's a roof where people have to access the roof much more frequently than just to do standard roof maintenance. It might be a roof with a lot of solar panels or equipment or machinery that need regular maintenance. If a designer wants to increase the compressive resistance of that roof concept, then this can be easily done by adding what we call a roof cover board. The roof cover board goes on top of the thermal insulation before the waterproofing is installed. This roof cover board will make the roof surface much more resistant to foot traffic, and it will also increase the fire resistance of the whole buildup. All these layers need to be fixed to the roof deck or roof structure. To do this, there is a whole array of different fastening techniques. One of them is mechanical fastening. This means that we use screws, pressure distribution plates, or polyamide tubes with screws to fix all these layers into the roof structure. Please note that you might need different screws for different types of substrates. In New Zealand, we will use stainless steel screws for plywood, and we have different screws for concrete or for structural steel. The number of screws will depend on the wind load calculation that is done following New Zealand Standard 1170 wind action that will determine the wind load design pressure on the different roof areas. This will then decide how many fixings we place per square meter. I will come back to that later on. Another method to install the thermal insulation on top of your structural roof deck is by using polyurethane adhesive. This adhesive is a non-penetrative way of fixing the thermal insulation board. But beware that these systems will have a maximum wind load resistance, in this case 5 kPa. So we have to verify the wind load design pressure before we can go ahead and use polyurethane adhesive as our fastening method for this roof concept. This brings us to the final component of the warm roof concept. The final layer of the warm roof system is the waterproofing membrane system. At Soprema, we have double layer and single layer systems available. The double layer system is a system that uses modified bitumen waterproofing membranes. The waterproofing system in a double layer system combines the base sheet and the cap sheet. The base sheet is installed on top of the thermal insulation as a first layer, which is self-adhered or mechanically fastened. The cap sheet is then installed on top of the base sheet while staggering the laps by two types of installation. One can be the torch-on application method using an open flame, or the flameless self-adhesive method. Both these systems are available in New Zealand. On this slide you can see pictures of different installation methods for the base sheet. On the left picture you can see the installation by mechanical fixing. The applicator will use pressure distribution plates and screws to fix the base sheet into the substrate. Please note that you need a specific screw for a specific substrate. For wood, for example, we use stainless steel screws. The distance between the fixings is determined by the wind load calculation and the resulting wind load design pressure following New Zealand Standard 1170 wind action. On the right hand, you see installation by self-adhesive application. Note that this membrane has stripes of sticky bitumen at the back that partially bond the membrane to the insulation layer. In those two-layer systems, the cap sheet is the finishing layer. This layer is normally finished with a colored aggregate, which is like a mineral chip or a granule stone, which is pressed into the top coating of the membrane in the factory. It comes to the roof as a finished product in a roll and is installed by a certified applicator. These membranes have to be very resistant to the outdoor climate. They have to be UV resistant, they have to resist the different climates, whether it's cold or hot temperatures, and they need to be fire retardant. In some cases, these cap sheets can have additional benefits, such as, for example, root retardance, if we want to continue and place a green roof on top. Another waterproofing system is the single-ply waterproofing system. This uses a single sheet of thermoplastic olefin or TPO waterproofing membranes. These membranes are typically made of very wide sheets and longer length rolls that are welded together on the roof by means of a hot air welding equipment tool. They have a smooth finish and they can be either fully adhered or mechanically fastened on top of the thermal insulation layer. We have now looked at all the different layers of a warm roof concept. When choosing a warm roof, you can take into account a different selection of design parameters. Some of these parameters might be as follows. What is the proven durability of this concept in New Zealand? What is the expected lifetime of serviceable lifetime of this concept? What is the material warranty that I will get? Is the system fire retardant or not? Has the system a built-in root protection if you want to add a green roof in the future? What about the aesthetical finishes? What colors are available? What about local and international certification? This can be very important when going through building consent or preparing your building consent package. Are there any environmental parameters I have to take into account? And finally, what is the engineering support I can expect? We are thinking here about the actual roof details or the engineering calculations like the wind load calculation or the condensation risk analysis, for example. Let us now have a look at the different engineering support that's available when designing a warm roof concept. If we look at the falls, it's important to understand that there is a difference between design fall and effective fall. The design fall is what we initially put on the drawing. The efficient or effective fall is what we will have after that the roof concept has been built and has been servicing us for a couple of years. So some substrates will have more deflection than others, for example, reinforced concrete compared to plywood. We have to take this into account, so that's why minimum design fall is quite important. There are different ways to find what is the minimum fall that is required. There might be the local regulations that have to be taken into account, or the local certifications that will point us in the right direction, or the minimum slope required by the manufacturer in order to give the right material warranty. So it's good to contact your supplier to see what minimum fall is required for this specific warm roof concept. When we talk about minimum fall requirements, it's also good to mention that polyisocyanurate and mineral wool boards can be purchased as tapered insulation boards. This means that the fall is within the thermal insulation layer. To achieve this, we need a copy of the roof plan with the drainage points and the indication of internal gutters with the minimum desired fall so that the tapered scheme can be designed. The tapered scheme is actually a puzzle that uses standard boards with a certain minimum fall to come together on a plan to form the gradient and the fall that you wish on your roof. This tapered scheme is available for both polyisocyanurate and mineral wool solutions. Warm roof concepts are lightweight. To give you an idea, if we look at a standard warm roof concept, we are talking around 12 to 13 kg per square meter. Also, the thickness can be obtained quite easily by adding all the thicknesses of the different materials, and this is interesting to know in your design phase when you are looking at your upstand height or clearance for certain machinery and equipment that might come on top of the roof. When we talk about weight and we talk about lightweight roof concepts, we have to make sure that they will be wind load resistant on the long term. For this, we are guided in New Zealand by the New Zealand Standard 1170 Wind Action. This standard will tell us how to calculate the wind load design pressure of a certain flat roof area. This needs to be done for every project, job specifically. Why? Because every project is different. The New Zealand standard, for example, describes the difference in importance level between buildings. The fact that every building is in a different location, it might be positioned on a hill. We have to take into account all these different parameters. As you can see, the topography of the location of our building will influence the actual wind load design pressure. For that reason, we make a job-specific wind load calculation for your project. We need to know the wind load design pressure because that relates back to the different ways of installation which I covered earlier in this presentation. When the wind load calculation is finished, we will put the results on the roof plan. The roof plan will show us the different wind load design pressures that we found for the corner areas, the edge areas RA1 and RA2, and the center of the roof. The wind load design pressure will be the lowest in the center of the roof and the highest in the corners. This means that we might have to use more fixings in the corners compared to the center of the roof. The distance between those fixings will be mentioned in the left bottom corner of your roof plan. This is information that the certified applicator needs to know in order to price the job more accurately. Another engineering calculation that can be done is the thermal analysis. In this analysis, we are going to prove the performance of the roof, and more specifically the thermal performance and the fact that there will be no long-term condensation risk within that warm roof concept. As you remember, the goal of a warm roof is to keep the dew point out of the structure and to create a very long-performing roof that creates energy cost efficiency by energy cost saving for the building owner. In our own thermal analysis, we will take the roof concept that you have designed or specified and look at each individual layer and its R value. This will give us the total R value of the roof concept. Following this, we are going to put that roof in the location where the project is going to be built. We take into account local climate data for the last 15 years, and we do a simulation of what the roof will do throughout a year, going through winter and summer. By doing this, we can now safely say that when we use the right vapor barrier and the right thickness of insulation, we have an interstitial and internal condensation risk-free roof. And this report signs off on that. When we have decided on the different layers of the warm roof concept, we now have to integrate them into the architectural drawings. This means that you might have to connect the warm roof system to other elements such as your upstand, your roof drain, skylights, and other equipments on the roof. For this reason, you can refer to the technical details by the manufacturer. Some manufacturers will also include job-specific detail service for more complex details such as, for example, seismic joints. The warm roof concept needs more than just the vapor control layer, the thermal insulation, and the waterproofing membrane. A good system will have a whole selection of smart accessories. For example, we have the roof edge profiles that make the membranes wind peel resistant but also give a nice straight finish to the membrane edge. We can have special pedestals that are not penetrating the waterproofing or thermal insulation to provide a support for solar panels on top of the flat roofs, or smart ways to deal with cables that go back into the roof structure by means of shrink sleeves. After we have designed the roof system and we have done all the engineering calculations and we have done a detailed review, we now have to prepare for building consent. This means that we have to make sure that we have all the right certification and attestation to accompany the warm roof specification, the warm roof proposal. For this reason, you can have a look at all the brand certificates and the code mark certificate for the Soprema warm roof systems. The minimum fall requirement for the bitumen waterproofing systems by Soprema is 1 degree. All the different systems are available on MasterSpec, so it's easy to select the membrane type of your choice, with or without thermal insulation as a warm roof concept. They can also be specified, of course, as a standard cold roof waterproofing system. Finally, I'd like to thank you for your attention. I hope it was interesting and that you learned a little bit more about warm roof concepts. Do not hesitate to have a look at the website of our distributor Equus Industries for more information. Thank you.